Today's lesson is not as complicated as some of your other ones with the matrices, so that's good. And it won't take us all class period, which is also good. If you did not grab a note sheet, they're on my desk. All right, so let's begin. We're talking today about determinants, and I want to begin by before I even tell you what they are, I want to tell you why we're going to talk about them, and I would like for you to write this down. This is the why for today's lesson. It's important to know your why. So the determinant is something that we're going to learn how to calculate today, and the value of it gives us very important information. Why we're learning about determinants is because if the determinant equals 0, after we do the math, which I will explain to you in just a bit, then the inverse of the matrix A negative 1, the inverse of A, does not exist. DNE does not exist. And therefore, or just write, and the equation AX equals B can't be solved. So this is, we talked last week about inverses and how they're used to solve equations, which we will do soon. We've only talked about how to find an inverse. We use inverses to solve. However, if you did your homework over the weekend or you were doing the homework or the work in class Friday, it was a moderate amount of effort to calculate the inverse. What this method will do, the determinant will show us if the inverse even exists. Because if it doesn't, we don't have to bother doing the math to find it. So the determinant will help us save some time and give us other kinds of information. And that's how I'm going to show you to solve for today. I need someone to please read all of these words out loud to the class. Volunteers? Yes, ma'am. And everyone else read it with your eyes while Emily reads it out loud. Yes. Thank you. What did that mean to y'all? Nothing? That was a lot of words, right? Okay. Let's break some of that down, and then I'm going to come back to it later in the lesson and show you that you knew what that meant. You just didn't realize you knew what that meant. The goal of today's lesson, our I will statement for today, is to evaluate the determinant of this 3x3 matrix. Okay, we're going to find the value of the determinant. But going back with these words, to subtract, what does that word subtract mean? Take away, right? Means subtract. What does sum mean? This is subtract. Sum means we'll be adding. Product means which operation? Multiply, all right? And we know what diagonals are, right? In a matrix, we have the diagonals. Okay. So the diagonal is going up from the sum of all the products of the diagonals going down. So these are the things that I have to define for you. What does that mean, diagonals going up? And what does it mean, diagonals going down? But the other words, we pretty much know what they mean. And we'll come back to this in a bit to sort of close the loop on all that wordiness. So here's where we're going to begin, with the determinant of a 2x2 matrix, which is actually very simple. This is the general notation. One thing that, before we even actually do the math, I want to show you the notation for determinant. There's two different options. This is one option. Okay, I have this matrix here, and when you see DET out front, it means find the determinant. It's telling you, figure out what it is, evaluate. The other option you could see is this option. What's different about this option means the exact same thing, but what are some differences between those two formats? It looks like absolute value bars. It's not the absolute value function, but it is straight bars instead of the bars with the feet in the heads. What else is different? What's different? Yeah, the brackets have changed. There's one other thing missing. The determinant, the DET. Okay, there's no DET written there. So if you see a matrix with straight lines, this is telling you you're finding the determinant of the matrix. Okay, this is two different formats, and that's why it's equal between them. You can either have DET and then the matrix written like normal with the brackets, or you can have the matrix inside what looks like absolute value bars, but you're not actually finding the absolute value. It's just symbolic. It's just notation. And then so what that actually equals, the math is, it's A times D, that's a down diagonal, minus C times B. So here's where the down and the up come into play. This is down, and then CB, this is up. And with a 2 by 2, that distinction is almost pointless. In the 3 by 3, it will be more necessary. So what we're going to do is find the difference of them. We're going to subtract the down products minus the up products. Is what we're going to do. Down minus up. And like I said, in 2 by 2, that distinction is almost pointless. But in 3 by 3, it will be more necessary. So if I'm finding the down products, here's my down diagonal starting at the top and working my way down. What two entries are on that diagonal? 3 and 4. So I'm going to multiply them. And I'll get 12. And then the up diagonal, starting at the bottom then, because you have to start at the bottom in order to go up. Which two entries are on that diagonal? 5, -1. And I'm doing what with those two numbers? Multiplying. And then what am I doing with those two things? Subtracting. So that's 12 minus -5. Two negatives make a positive, and we get 17. And then I'm done with the problem. It just said find the determinant. The determinant is 17. But just as a quick reference, why do we even care about the determinant? I really don't care that it's 17. I care about it in what way? That it's not 0. Very good. Okay? Because if it was 0, then my inverse would not exist, and I would not be able to solve any equation that this matrix would be part of. All right. So that was the downs minus the ups. 2 by 2, pretty much candy. Let's talk about how you do a 3 by 3. So we have this. The thing about a 3 by 3 matrix is a diagonal needs to have 3 entries. Don't write this out on your paper, but this is a clear diagonal right here. Okay? But if I keep trying to find more, that only takes into account these 3 entries. I need all the entries to be accounted for in my calculation, but I'm running out of room. These aren't proper diagonals right here. This only has 2 terms, and this only has 1. The way we can account for that is to do this. Take these first 2 columns, write your original matrix, and bring these columns out to the right-hand side of it, okay? Because then what happens is now I can take diagonals all the way across without running out of entries. And let me show you what I'm talking about. Remember I told you that we're doing the downs minus the ups. And here's how you find your down diagonals. You're starting at the top because you have to start at the top in order to go down. So if I'm starting here, I have this main diagonal that I would have had no matter what. A, E, I. And we're finding the product of them. Product means to do what? Multiply. So that's what's going on right here in this formula. A, E, I. A times E times I. So I'm going to move over and do the next diagonal. And I'm going to find the product of them, B, F, G. And then I can do one more diagonal before I run out of entries again. C, D, H, right here. C, D, H. So these are the products of the diagonals, and then they're being added together. That's just for all my down diagonals. So moving over and starting to do the up diagonals, where do you think I'm going to begin? Which letter? G, right? The farthest bottom left. So where am I going to go for that diagonal? G, E, C, right here. The product of those terms, those entries. And then moving to the right, H, F, A, right there. And then moving to the right one more time before I run out of entries, I, D, B. So all you're doing is multiplying all the entries on the diagonal. You're going to add them, and then when you get those two things, you'll subtract. So going back to the slide, a couple of slides, I'll put this slide back up, so don't freak out if you miss something. Here's what we are doing. Subtract the sum of the products of all of the diagonals going up from the sum of all the products of the diagonals going down. That's what we're doing. That's what that formula is, this, in symbols. Okay. Does anybody need this up anymore before we do the problem, the example problem? So we've got this 3 by 3 matrix. It says evaluate the determinant. Evaluate means find the value of the determinant. What was the very first step that we just talked about in the last slide? Perfect. Perfect. Take the first 2 columns and write them out here. And are we doing down minus up or ups minus downs? Downs minus the ups. I want you to take a second, preferably with a pencil, and I just want you to draw a line through your down diagonals, what you think that means to be down diagonals. You don't even have to do any math. I just want to be sure we're all clear on the definitions. What was your first down diagonal? 3, 4, 5. Very good. So we have 3, 4, 5. So we're doing what with those numbers in that diagonal? Multiplying. What was your next diagonal that's going down? Good. Negative 1, 6, 2. And we're multiplying those. And what was your third diagonal? 2, 1, 3. Good. 2 times 1 times 3. So when we do that math, this is 60, negative 12, 6, and what are we doing with those things? Adding. We're taking the sum of them. And then negative 12 and 6, negative 6 from 60, 54. Are we done with this problem? No, we just did the downs. What do we have to do now? The ups. What's your first up diagonal? 2, 4, 2. So and those numbers are getting multiplied. What's your next up diagonal? 3, 6, 3. in your last up diagonal. 5, 1, negative 1. Yep. So multiply those together. Add them. So my ups are 54. I'm sorry, my downs are 54, my ups are 65. What am I doing with those two things? Subtracting. Then 54 minus 65 is negative 11. Am I done, or is this a yes or no question? I'm done. Because it said evaluate, that just means find the value. But if this question was asking me, does this matrix have an inverse, what would you say? Yes. Yes. Under what condition does it not have an inverse? If it was 0, right? So we have one more problem. It's so easy. Does anybody need this up anymore? This says, write each system in the form of a matrix equation, do not solve. So here's where we start leading ourselves into solving equation and being able to just set up a matrix equation. We're basically rewriting this to look like some matrix A times some other matrix X equals some matrix B. What you want to do is set up your coefficient matrix. So negative 1, 2, negative 3. By the way, this is not a 0 here. Remember, if it's a 0, there's nothing there. It's a negative 1 there. And then 2, negative 1, 5, 1, negative 3, 0. That's all my coefficients. And please also notice I'm not setting up an augmented matrix. It's a matrix equation. So we have this matrix A. Then we need a matrix X. That's a matrix made up of variables. What are the variables in my system? X, Y, Z. Why do you think they're going vertically like that? Why do you think I wrote them vertically? What did you just have a skill check on? Multiplying, right? And when you're multiplying matrices, and then let's go ahead and put our constants here, and then I'll talk about it. Because it kind of feels like the X, Y, Z's all went left to right, because they did, right, in the system. But if you were to go do your matrix multiplication on the way I've written it right here, if you did your row by column, what are you multiplying? You're multiplying the first entries, negative X, the second entries, 2Y, the third entries, negative 3Z, and doing what with those things? Yes, right there. Where are you even coming from? Were you in the lounge? Oh, okay. Yes, anything for you, Miss Bueller. You're welcome. It's my pleasure. So the dot product is we multiply those things together and then do what with them? Add them, right? And that's going to equal the entry in the first row, first column, which happens to be 7. So you see how if I did the matrix multiplication all the way back through? Bye. You're welcome. It would look just like the system? Yes, the system? You? Yes or no? I think that's kind of cool. I like that. So that is the end of your notes. Let me give you your homework.